Let's work on example 17.4, which involves the intermediate value theorem and Newton's method to estimate where a function will return a certain value. So it's a pretty cool problem. It ties in a lot of results. Let's consider the function f of x, which is x cubed minus x. First, we want to justify that the function crosses the line y is equal to 1 somewhere between x is equal to 1 and x is equal to 2. So this to me screams intermediate value theorem. So somewhere between, if I can draw a graph up here, somewhere between x is equal to 1 and x is equal to 2, I'm saying that we are going to cross the line y is equal to 1. So if I evaluate my function at 1, by plugging 1 in here, we have 0. If I evaluate my function at 2, by plugging 2 in here, we have f of 2 being 6. So this is up here at 6. So this is a continuous function that connects this point to this point. So it has to cross the line y is equal to 1. This is by the intermediate value theorem. So by the intermediate value theorem, there exists a c value somewhere between 1 and 2, right? There's some value inside 1 and 2 where your function at that point crosses the line y is equal to 1. It gives you a y value of 1. So now the second part asks us to find that c value, approximate the point where the function returns a 1. And it says that we should use Newton's method. Now, Newton's method is a way to find the zeros of functions. So I'm going to create a new function. I'm going to call it g of x, and it will be f of x minus 1. So it will be x cubed minus x minus 1. And the reason I do this is because if I'm looking for where my f function gives me a 1, then that's the same thing as my g function returning a 0. And that's what Newton's method can find for me. Right? Newton's method will find the 0 of g, which by the definition of g will be where my function f returns a value of 1. Okay, so my Newton's method says that xn is found by xn minus 1 minus f at xn minus 1 over f prime at xn minus 1. Right, this is the recursive definition. This is the pattern. So I'm going to need my derivative. Let's look at g prime. This is 3x squared minus 1. So we need a first guess to kick off this method. And I'm going to let my first guess be just the value of 1. So I know it's not where my value is supposed to be, right? That's where my function f is 0, not 1. But if I let this be my first guess, then Newton's method is going to tell me my next guess is 1 minus g at 1 over g prime at 1. Right? I'm using the g function because Newton's method finds me the zeros of functions, and g is the function where I'm looking for the 0. Now, run through this algebra, you find that x1 is going to be 1.5. So now we do this again. x2 is found by taking x1 minus g at x1 over g prime at x1. So this is 1.5 minus g at 1.5 over g prime at 1.5. So plugging this into a calculator, we can evaluate this. Our second guess, x2, is 1.3478, roughly. All right, so we went from x0 to x1. We went from x1 to x2. And it wants 3 iterations. So we'll go to x3. x3 is given to us by x2 minus our function at x2 divided by its derivative at x2. So this is 1.3478 minus g at 1.3478 divided by g prime at 1.3478. And running through this algebra by evaluating your function and its derivative at x2, x3 is about 1.3252. So this right here is a good estimate for the 0 of g, which by the definition of g is going to be the x value where our function f returns a 1, and that's what we were looking for. So about 1.3252. If I can go to my picture, it turns out the point we're looking for is 1.3252. That's the value where our f function gives us a value of 1.